Hello everyone, I'm going to do problem 8 on the physics homework. A particle of charge uppercase Q lies midway between two identical fixed charges, each having a charge of lowercase q and separated by a distance 2b. A. What is the net force on uppercase Q when it is midway between the two fixed charges? B. Suppose Q is displaced from the midpoint by amount x as shown in the sketch. If uppercase Q and lowercase q have like signs, find the net force. And C. If x is a lot smaller than b, and if the particle is released from its position shown in the sketch, it would oscillate with simple harmonic motion with what angular frequency? So here's the sketch. First we want to find the net force of Q when it's midway between the fixed charges. Note I didn't put the charge, the exact charge on each forces, whether it's positive or negative, because that doesn't really matter. You see, if lowercase q was negative, then lowercase q over q was negative, and if uppercase q was positive, then these charges will be going this way, this one will go that way, or if this was positive and this was positive, this would be the force, and same thing like that. Also note that x in this case is positive as we go to the right. So using simple for a sum of forces, we get kq over q1 over b squared plus negative kq uppercase q lowercase q over b squared. And since both q1 and q2 are the same, they cancel out and you get 0. Next, suppose that Q is displaced from the midpoint by an amount x as shown in the sketch. If uppercase Q and lowercase q have like signs, what is the net force on Q? Okay, so again I didn't put the charge because, if this was positive, and then this was positive, and then that was positive, the forces will still, or if this was negative and this was negative and this was negative, the forces will just, the magnitude of the forces will equal each other. And so the direction actually. So I made a simple force diagram showing that the forces on this one and on Q1 and Q2 we don't care about. We only care about the force on the uppercase Q. And the only difference between this and the last example is this one has a different distance from b plus x and b minus x over here. So simply, again, sum of forces equals kq uppercase q lowercase q, I remove, and then multiply by 1 over b, which is distance plus x squared, minus 1 over b minus x squared. Alright. And then we're just going to simplify this portion first. So we do a bit of get the bases to become the same, factor out the, or distribute the squares to get those polynomials. Then you subtract the tops and you get negative 4xb over all this. And then you can simplify the bottom by getting these sum of squares, or yeah. And then you can simplify those to get this. You can keep going. And now we're going to take this, put it back into the original equation, multiply again by k uppercase q lowercase q. And we get force, we take the k constant and we simplify it to 1 over 4 pi e naught. And then the force cancel out, left with negative xb uppercase q lowercase q over pi 8 epsilon b squared minus x squared, all of that squared. And now C, we want to find if x is a lot smaller than b, and if the particle is released from its position shown in the sketch, what is the angular frequency of the particle given as m as the mass of the particle? So here, force equals ma, m being the mass of the particle. Now let's solve this. So mass acceleration, sorry, is also the second derivative of position. And we already solved for force beforehand, so I'm just plugging that in. So do a bit of simplification, you get this, and note I got rid of the minus sign because it's not necessary. It's because this object is going back and forth like this. The minus sign doesn't really matter. And so now I just change the sides. So we got the second derivative of position on this side. And since we know that the second derivative of position, omega squared, is equal to that times an x, we just got rid of that x over here, and here's omega squared. Square root both sides, omega equals the square root of all of this. And note that since x is a lot smaller than b, if you subtract x from b, you basically gotta get b. The x is gonna be a very, very small number and probably not matter. So then we can do some simplification with the b's, and you get that. There's your angular momentum. Thank you.